Welcome back, Focus Learner. I am absolutely thrilled you're tuning in for today's explainer. You know, we hear about AI everywhere. We wonder how machines can suddenly recognize faces, or translate languages on the fly, or just generate entirely new text out of thin air. Well, it's all thanks to the absolute magic of artificial neural networks. Now, if you've ever felt completely intimidated by the dense math and the programming jargon that usually surrounds AI, honestly, just leave it at the door. Seriously. Today, we're stripping all of that away. We're going to replace the heavy calculus with simple, everyday analogies so you can see exactly how the artificial brain actually works. Okay, let's dive into our roadmap for this explainer. We'll start by meeting the artificial brain. Then we'll break down the party decision and build the layer sandwich. After that, we'll see how these networks are learning from mistakes, check out neural networks in action, and finally look at the future of AI.
Section 1. Meet the artificial brain. To really get a grip on this technology, we actually have to start with your own head. At its core, an artificial neural network, or ANN, is a computational model that's completely inspired by the structure and the functioning of the biological brain. It is essentially this massive network designed to recognize complex patterns and relationships hidden in data. So whether we're talking about the systems that recommend your next binge watch or the incredibly powerful large language models powering today's advanced chatbots, this foundational framework right here forms their brain. They learn from experience, literally adjusting themselves as they are exposed to more and more information.
Think about the immense scale of our own biological networks. The human brain is this incredibly dense network of roughly 100 billion biological neurons, and they're all connected by synapses. Now, compare that to the artificial brain. Instead of biological cells, it uses artificial nodes, which are, essentially just mathematical functions. And instead of physical synapses linking everything together, these artificial nodes are connected by what we call weighted numerical edges. It's literally a mathematical abstraction of our biology. But to really grasp how this massive network functions, we have to zoom all the way in on just one of those artificial nodes.
Section 2. The party decision. Let's isolate a single artificial neuron for a second. I want you to imagine that this neuron is just you, and you're trying to make a really simple decision. Should you go to a party tonight? This is such a relatable analogy straight from our sources, and it beautifully strips away all the complex math. Your brain takes in different pieces of information to make that choice, right? Well, an artificial neuron does the exact same thing. The pieces of information you consider, those are your inputs. For our party decision, let's just say there are only two factors that really matter to you. First up, are you tired? We're going to call that input X0. Second, are your best friends going to be there? We'll call that input X1. In the world of our artificial neuron, these are just super simple yes or no questions. The network simply encodes a yes as a 1 and a no as a 0. But obviously, not all inputs are equally important to your final decision, are they? And that brings us to the sometimes intimidating jargon of weights and biases. But honestly, they're incredibly simple. A weight just represents how much you care about a specific factor. Like maybe you're a little bit tired, but if your absolute best friends are going, you care about that way more. So that input gets a higher weight. A bias, on the other hand, is just your baseline mood. Are you a total social butterfly who just wants to go to the party regardless of the other inputs? That right there is a high bias. If the combined total of your inputs, multiplied by how much you care about them, your weights, plus your baseline mood, your bias, crosses a certain threshold, boom, the neuron fires and you decide to go to the party.
Section 3, stacking the layer sandwich. Okay, so now we know how a single neuron makes one isolated choice. But what happens when we chain thousands or even millions of them together? Try thinking of a massive neural network's architecture physically, like a sandwich. It's really the easiest way to ground the concept of how data flows. The top bun is the input layer. That's where raw data, like the actual pixels of an image, enters the system. Then we have the filling, the hidden layers. This is where all the heavy computation and the real pattern recognition happens. And finally, the bottom bun is the output layer, which delivers the network's final prediction or decision.
So the absolutely crucial point is what happens inside that filling, those hidden layers. This is where the network builds complex abstractions. For example, if you feed an image of a handwritten number into the top bun, the first hidden layer might just detect very primitive edges. That's it. But then the next layer takes those edges and identifies contours. The layer after that turns those contours into shapes. And finally, the last layer associates those specific shapes with an actual number. Every single layer works on the abstraction of the previous one, making increasingly complex decisions. But here is the big question. How does it actually know if it made the right decision?
Section 4. Learning from mistakes. Just like us, these networks aren't born knowing all the answers. They literally have to learn by making mistakes. So here is how our artificial sandwich actually gets smarter over time. First, there's the forward pass. This is where the network takes an input and just makes its best guess. Then, the loss function kicks in to check its work against the correct answer, basically calculating how massive its error was. Now, a highly intimidating term comes into play here, called backpropagation. But please, do not let that scare you. Backpropagation is simply the network working backward from its mistake to figure out exactly which neurons were responsible for the bad guess. Finally, we have gradient descent. This is where the network tweaks its weights and biases, essentially adjusting its party rules, so it makes a better guess the next time around. It just repeats the cycle millions of times until it becomes an absolute expert.
Section 5, Neural Networks in Action.
All right, so we've got our neurons, we've stacked them into a sandwich, and we've trained them to learn from their mistakes. Let's look at how these fully trained networks are actually deployed into the real world to solve human problems. What's really fascinating here is how different network architectures have evolved to specialize in completely different tasks. For instance, think of convolutional neural networks, or CNNs, as the eyes. They're the absolute gold standard for image processing, achieving incredible things like identifying skin cancer from medical images with over 94% accuracy. Then you have recurrent neural networks, or RNNs, which act more like the ears. They are built specifically for sequences, making them absolutely perfect for things like speech recognition and translation. And then we have transformers. These are like the mouth and really the modern conversational brain. They've abandoned older methods so they can process massive amounts of text all at once. Transformers are the exact architecture powering the incredibly capable large language models and chatbots that we all use today.
Section 6, The Future of AI.
These architectures are completely revolutionizing our daily workflows, no doubt about it. But this immense power comes with a very real physical cost. The brute force pattern recognition required to train and run these massive neural networks requires a staggering amount of energy. Get this, in 2024, AI systems and data centers in the US consumed approximately 415 terawatt hours of power. That is over 10% of the entire nation's total electricity production. And as these models become even more complex, that energy consumption is literally projected to double by 2030. We are facing a very real scenario where the digital brains we're building are putting an immense strain on our physical resources.
But researchers know this current energy path is totally unsustainable, which brings us to an incredibly exciting glimpse of the future. Recently, a team at Tufts University unveiled a groundbreaking approach called neurosymbolic AI. Now, conventional AI uses a ton of energy to just blindly search for patterns. Neurosymbolic AI, however, combines that pattern recognition with abstract logical rules, really mimicking human-like reasoning. In their tests, this new system achieved a 95% success rate on complex tasks. And here is the absolute kicker. It did so using only 1% of the typical training energy. Talk about a game changer.
It's an incredible breakthrough, and it leaves us with a really provocative thought to end on today. We've seen exactly how the artificial brain works, right? From a single neuron making a simple party decision all the way up to a massive layer sandwich that's transforming entire industries. But as we push the boundaries of what neural networks can do, the next great challenge isn't just making them smarter, it's making them sustainable. So will neurosymbolic models, or perhaps some entirely new architecture, save us from an AI energy crisis? It is exactly the question the brightest minds in the world are trying to answer right now. Thank you so much for joining me on this Explainer Focus Learner. I really hope you found this breakdown of neural networks illuminating. Keep learning, stay curious, and I'll see you next time.